Thanks to both you and Naresh for inviting me here. It's a real pleasure to be speaking before this crowd. And when I was thinking about my keynote, I really wanted to take a broad approach, especially since I knew that there would be a lot of students here. So I wanted to provide some perspective on my own experiences over the course of the past decade or so. And I don't want to be too super formal about this. If you do have any questions or I'm unclear about anything, feel free to jump in and ask me something or anything. All right, so let's get started here. Okay, so the title of my talk is, Can Music Cognition Help Us Build Better Computer Music Software? I hope that I can partially answer that question by the end of my talk, but it's still an open question, so here we go. Okay, so today I'm going to talk about several research projects that encompass very different goals, methodologies, and applications. Or at least they might seem that way if they're viewed separately. They range from a computer music application, HyperScore, which Frank mentioned, to cognitive psychology experiments in music cognition in particular, and some MIR research as well. So from a disciplinary perspective, they seem fairly unrelated. And I will begin by talking about HyperScore first, the graphical computer-assisted composition system that I developed. And that was a system that was based on visualizing musical tension originally. So that's almost a separate project from some of the music cognition experiments that I've done after developing the system. But they are actually interconnected in some ways. So I will talk about a series of experiments I conducted to explore in depth how listeners perceive tension, and my attempts to model the resulting empirical data. I will also talk about algorithms, this is more in the MIR realm, for extracting melodic patterns from music, also known in music theory parlance as motives. And then I will tie all this research together by discussing how these different strands might come together in a computer music system that's similar in context to with regard to HyperScore. So that's kind of the overview of what I'm going to talk about today. As I talk about these projects, I'm going to intersperse them with some commentary about methodological issues that I encountered with regard to combining engineering and computer science approaches with cognitive science approaches. And yes, it's been difficult in some ways, but I think I've managed to at least use different strands from each disciplinary perspective in a complementary sort of way. And I don't pretend to know everything about this, and I can't say that it's easy to merge or even possible to merge these aspects or these approaches. But hopefully what I've done might provide some perspective for you. And just to clarify, when I refer to this dichotomy, those two methods, I do so pretty generically. So, well, that is, MIR uses more computational approaches that involve signal processing, machine learning, that sort of perspective, while music cognition methods, of course, revolve around collecting empirical data, so seeing how human listeners respond to music. Okay, so I'll begin by talking about HyperScore. HyperScore is a fairly old project. This is something I worked on when I was a PhD student. It's a graphical computer-assisted composition system that was designed for users with little or no musical training. And the idea is that the graphical language that's used in HyperScore is supposed to describe structure in music. And the input from the user occurs at the lowest and highest levels of abstraction. So at the low level, you have musical patterns or the motives. So that's the basic building blocks of how HyperScore works. And then you have the large-scale shape of the piece, which you can see just by looking at the sketch that the user draws. However, the concept of shaping musical tension was really the important part of the genesis of HyperScore. So I'm going to step through some of the original versions, the oldest versions of HyperScore, and then give a demo of what ended up being the final prototype, so you have an idea of the progression of thinking here. Okay, so the first prototype was pretty basic. It was almost a completely automated system. And the user input consisted of a tension line that was drawn by the user. The user then selected a bunch of precomposed motives, and the system produced some music that matched the tension profile described in that line the user drew. So the line was parsed for parabolic shapes and local texture, and those were kind of the inputs to this pretty basic algorithm. But the problem with this is that it was definitely very automated. Although the user did have this sort of high-level input and could select a few patterns, it was not very interesting. It was more of an experiment than anything else. And as HyperScore progressed, it became more of a free hand drawing interface with more user control. So as HyperScore progresses, it's all about giving the user more control, and it kind of goes away from the idea of having a completely automated system or almost completely automated system. And included adding a central timeline that was drawn by the user. And you see in this particular version, get my mouse pointer here, this is the timeline in the middle. So it could kind of even wrap around itself. Not very practical, actually. And I added, I kept the precomposed motives, but I added the idea of drawing in colors that were mapped to these motives, and the system would take the proximity of these annotations and basically compose the piece based on this input. I also added some harmonization algorithms based on a simple Markov model, but it was still really kind of too automated. It was a little more interesting, but it wasn't interesting enough, at least for the user. And so HyperScore progressed. Precomposed motives became user-composed motives. I had, various types of harmonization algorithms that could be applied. And increasingly, I realized that the problem with these versions of HyperScore was this very limited space in which to draw. And also you drew the timeline, and what ended up happening is if you really wanted to compose something, you had to draw a very straight line, because having something that's this freeform actually doesn't work very well. So HyperScore progressed into more of an infinite canvas where you could kind of move around anywhere and start drawing stuff. And that was a little bit too infinite, I think, in the sense that it really became sort of random. And this is kind of a transition phase where we decided we wanted to use 3D graphics just for the hardware acceleration. This is, by the way, this was a Windows application, and it was written using DirectX, and it was written in C++, just to give you some context. Okay, so what I'm going to do is demo the final, what I call the final version of HyperScore. Let me let's see. Here we are. Okay. So this is what HyperScore looks like, or looked like at the end. And as I mentioned, there are these two forms of input, the motivic material and then the sketch. So the motivic material looks like this. It's a simple piano roll grid where you plop in some notes. You can move them around, you can make them longer or shorter. Just going to make something simple and rhythmic. Can you hear that? Is the volume good? Okay. And the idea was, so you'd pick a color, to map to this particular pattern. I like blue. I'll just keep blue here. And then you could sketch that particular pattern in by drawing that color into the window. So I'm just going to draw a very straight line here. And what you'll hear is this particular pattern repeated. It's very simple. And then when you start to do things like shape that line, then you get kind of an overarching, then you get an overarching contour that's imposed on the repetitions. So here we go. Something like this. So it's not a literal envelope that's applied onto these repetitions. It's more rather, the algorithm tries to keep the shape of the actual pattern so that it's not completely warped to a point that you don't recognize the individual contours anymore. Okay, so as you can see, it's very easy just kind of draw stuff with hyperscore. I mean, you can scribble all sorts of stuff, have something that sounds very contrapuntal very quickly. Okay, so here's my masterpiece. It doesn't look very good. I'm gonna delete that. I'm gonna make it, yeah, that's it. Okay, so I'm gonna play this piece, and what you'll hear is a lot of kind of atonal sounding rhythmic stuff. But you can generate material quickly with hyperscore. That's the point.
The part was coming up. Scoop in the middle.
So I mentioned that originally my intent for the system was to be able to model musical tension in some way, or generate music based on tension. That particular concept was sort of retained in this final version. And in this version, instead of having a general tension line, there's a harmonic tension line, which is in the middle. So the idea is that you can shape this line, and you can see that as I kind of move stuff around, these colored bars appear. And the colored bars represent different colored or different types of harmonic phrases, for lack of a better term, where the green and blue up-down sections are antecedent consequent type harmonizations, and then you have modulation sections, which are these kind of pointy regions that are colored yellow or orange, or I don't know, some combination of both. So I'm going to, and the idea is that the position of these points from the center line denote exactly how far from the starting key you modulate. Okay, so I'm going to play this now with this harmonization button turned on, and you'll see that it's been transformed into the melodic material has been transformed to fit this particular progression that's been generated. Because the user was supposed to be a novice in this case, and that's what the software was used for. And in fact, this final version was used mostly with children in a big project with symphony orchestras, and that was the big project that my advisor at MIT did. So this was one of the things within that project. Anyway, what was nice about the software was that, you know, novices could really be creative with it, even if they had no musical training. And I just want to play a very short, not all of these, but just excerpts from some of the things that the kids over the past several years have written using the software. And this, for example, was written by a kid using, oh, yeah, you know what? My virus protection program has taken over my machine. I really apologize. Every 20 minutes, this thing comes up. I've tried to turn it off, and it turns itself back on. And there's nothing I can do. So anyway, I apologize. And so this kid basically had very simple motives and put them together in a way that worked very well with the harmony line. So you get the idea. It's a very creative use of the harmony line. And then there were other examples which were more kind of textural or orchestral, I guess. Compositions which were very different, and the users would basically use hyperscore as a sequencer, more or less. And so on. And then these kind of weird hybrids, like this person wrote a funky transcription of Feralisa, which is kind of cute. I'll play it because I like it. Of what HyperScore did, but as you can see, it really moved away from its original intent as an algorithmic composition system that shaped tension based on tension curves drawn by the user in the generic sense. While it did technically have that harmony tension line, its development did not further my original intent, really. It became more of a practical tool than anything else instead of something that had a more theoretical basis. And I realized at this point, to really solve this tension problem, which was bothering me because I felt I really didn't understand what was going on in the listener's mind when they were processing music and kind of deriving a sense of overall tension, that I really had to approach this problem in a scientific manner. Okay, so let me go back to presentation. Okay, so here's the question. How do you model tension? Well, you can look at it first and kind of break it down into its component parts. So clearly there are musical features and expressive features that contribute to tension. So for example, pitch, harmony, key, melodic structures, all of those things might contribute to tension. Also, what performers do, so dynamics, tempo variations, all of those things affect listeners' perceptions. So I assumed that tension was a function of these features. But the question was, how do you actually define and quantify the effect of individual features and how they interact on tension as perceived by the listener? So at that point, I embarked on a series of experiments. I conducted 2 tension experiments that explored the contributions of a whole bunch of features: harmony, pitch height, melodic expectation, onset frequency, rhythmic regularity, tempo, dynamics, and loudness. And that was about it. So the first tension experiment was a web-based study with approximately 3,000 subjects. The stimuli were designed to systematically combine and isolate individual musical features. And my goal was to verify the impact of these individual features and then to gain some insight into their relative importance. For example, I figured, well, loudness is probably pretty important to tension, but maybe it's a little more important than a feature like harmony, maybe. Or maybe not, it might interact in some interesting way. So here are some of the simple stimuli that I composed for this web experiment. So for example, this was one stimulus that was just focused on tempo changes. Loudness changing. And then I would combine features that were kind of going in different directions, that were counteracting each other. And then there were some more obvious examples, like this one. Examples like this one, where you have, for example, the second chord leading to the third chord, it clearly resolves, but at the same time the melodic line goes up. So the question is, well, how much does the contour affect the feeling of resolution? case, there were differences between musicians and non-musicians, and only in the case of harmony, which was very interesting. Okay, so the choices, the possible answers or responses that they could select in the web experiment were described by graphs in order to provide intuitive, concise representations instead of wordy descriptions. So that was the idea behind these responses, as you see, are pretty straightforward curves. Well, except maybe this one. Now, what's interesting is that the results of this web study indicated that listeners clearly related changes in tension to all of those features, with the exception of rhythmic regularity. That's the only one that really didn't yield any results. In more complex stimuli where you had these counteractive effects, there was definitely confusion on the part of the listeners, and so there was no real clear trend necessarily, unless there was one particular feature that stood out. And then when they were in parallel, they really strengthened each other in terms of one direction or another. So that was the web study. However, that was not enough for what I needed to do. So I ran a more typical or traditional music cognition experiment with 35 subjects from MIT. And in this case, the stimuli were longer, they were more complex. They were, in this case, real musical excerpts, around a minute in length, maybe. They were rendered in MIDI, but they were tweaked so they sounded a little more expressive, especially with regard to dynamics. And then I collected real-time responses, so slider responses to the stimuli. Okay, I want to pause for a second with my first commentary, which is understanding experimental design. While I was a student at MIT, I certainly learned a lot about software development. But unfortunately, I knew next to nothing about running experiments. And of course, music cognition as a field is highly interdisciplinary, and collaborations among researchers coming from different disciplines is the norm. And in this case, I did collaborate with a psychologist. Some of you might know him, Josh McDermott. He's now a professor at MIT, and he does a lot of very interesting auditory perception research. But we actually did not collaborate in terms of experimental design. We each had our own experiments that we wanted to run, but we wanted to pool our resources together and hire an undergraduate programmer, which sounded like a good idea at the time. So we designed our own experiments. We had the single website that had featured both experiments that was implemented by this undergraduate. And let's just say there was a bug. And the bug was disastrous, but only for my experiment, as it turned out. And it was such a weird, subtle bug that even when I tested it and I thought everything was okay, I only learned about this problem when I looked at the data after all of it had been collected. And I was like, this is kind of weird. And then I looked at the code, and it was such a simple bug. Long story short, I had to throw out half of my data. So instead of 6,000 subjects, I ended up having 3,000, which was a very bad day, by the way. So I learned some hard lessons from this experience. It was an unfortunate error, and what I learned was this: you can't just double check things. You need to triple and quadruple check them, especially if you're collaborating with others and you're dependent on what they do. And of course I could have written this thing myself. That was not an issue. It was more a matter of time. And in collaborations, everyone does contribute something, hopefully. And so this was kind of a new experience for me. And of course, designing these experiments was difficult for me at first because I had no knowledge of how to do this, and I certainly had no experience. And I feel fortunate that in the end, the data I collected, the data were fine, and I was able to use them for what I needed to do, which was design my attention model. But I think part of it was luck also. It could have just easily gone the other way. And in fact, I've run dozens of experiments since then, and some of them have failed miserably. So, I don't know. This is just a commentary on the very first lesson I learned about this sort of interdisciplinary approach. Okay, let's go back to the attention experiments. So at this point I had a lot of data, which is good. And once I had the continuous response data in particular, I wanted to use quantitative descriptions of each musical feature to model those responses. So that meant quantifying pitch height, tempo, onset frequency, which are one-dimensional and relatively straightforward. Loudness, I quantified using a psychoacoustic loudness model. Harmonic tension, I derived from Lerdahl's tonal tension model minus the melodic attraction component. And then I used Margulis's model to derive melodic expectation values. So I took all of those feature graphs, let's call them, or feature descriptions, and I wanted to model the mean tension response for each of these excerpts from the study. So you can see in this graph, the mean tension response is that black line in the middle, and all the other colored lines are the various descriptions of the features that I was testing. So it looks pretty crazy. So my goal was to define a mathematical model that, given the description of individual parameters, would produce an accurate global tension prediction. So my first idea was pretty straightforward. I said, well, I can try to fit linear and nonlinear models to a portion of the empirical data, given the musical features, and then try to predict the remaining data using that resulting model. So this is a very basic machine learning approach. And I thought, oh, well, maybe I might get some good results. So each model was tested on at least 75% of the data, and oftentimes 90% of the data for each excerpt. Was trained on that data and then tested on the rest of it in order to evaluate the model's usefulness. So as you can see, my use of regression is very different from how a typical psychologist would use regression, say, to analyze their data.
Sorry, Mary.
Yes?
Can I just interrupt?
Mm-hmm.
So the dependent variable is the black line.
Yes.
So how did you, because you've got different models contributing to that black line, which are very different in scale. So how did you weight those to create this dependent variable?
Very good question. I will get to that in a moment, but not in the case of the regression. In terms of weights, the regression model is going to produce those weights.
Of course.
But later on, that was a very important question. So hold on for a moment and I will get to that. Okay, so as you see, the results were terrible for both the linear and the quadratic. That's what I tested. Models. You can see that the quadratic model actually fits the training data quite well, which perhaps is expected, but it's certainly a case of overfitting because it blows up on the test data. And the linear model, not so good either. So I was disappointed, and maybe I had high expectations. But at that point, I felt, I really needed to step back for a moment. So here's my commentary number 2. It's nice to have empirical data, but how do you use it to build a predictive model, in this case a predictive tension model? Well, of course it's, dependent on what the problem is, which could be very different. And as I mentioned, my first attempt was to use a very typical machine learning technique. But here's the problem, the primary problem with the method that I used was that regression is not designed to capture the moment-to-moment effect that music has on a listener. It's not meant to do that. So it doesn't have this real-time aspect to it. That's important, I think, from a cognitive perspective. So at this point, I was like, okay, I'm going to rethink my approach completely. And I asked myself, well, is there a way that I might be able to incorporate all these disparate musical features that are contributing to tension in a way that reflects memory to some extent? So short-term or working memory. Okay, so one thing I noted from previous experiments was the importance of trends. Listeners really seemed to be attuned to clear trends. When I say trend, I mean, for example, ramps, like a clear crescendo, or a clear increase in tempo or decrease in tempo. So this idea of trend salience informed the basis of my next approach, which I'm referring to as a temporal model because it was designed to take into account the real-time aspects of listening. So this model includes 3 major components: an attentional window, which models a perceptual moving window in time and extracts a current tension trend, and then a memory window, which I simply defined as the direction of the tension trend in a window of time immediately preceding the attentional window. And then there's a lot I could talk about this, but basically there were weights for each of these individual features. So to answer Matthew's questions, yes, I did consider the weights. And the weights were based on the empirical data from my web experiment. Because I had these very isolated examples of one feature kind of clashing with another feature, which one does a listener actually hear most strongly. So based on that empirical data, I decided, okay, well, it made most sense to weight dynamics and pitch height the most. So they were given the highest weight, followed by tempo and onset frequency, and then harmony and pitch height of the inner lines and the bass. So that's where the weights came in. But this is perhaps a discussion for another day, but I'm not a really big fan of using weights. In fact, I don't think this is really the right approach. But this was my first approach. And I can get into more detail if any of you are interested in talking to me about what I did after this, because I'm not going to completely spend the rest of this talk about my tension model. But there are other ways of dealing with this issue of weighting features. Okay, so the feature descriptions serving as inputs to this new temporal model were the same as that were used for the regression model that I just talked about. The only feature I did not include was melodic expectation because it didn't correspond in a clear directional way with tension. Oh no. Oh yes. Oh. Okay. All right, here's a quick description of the temporal model. So the temporal model essentially defines tension as a function of musical features by estimating the combined directional or cumulative directional change of all the features in each attentional window. The combined directional change, or this tension trend, for an attentional window is also weighted by both what immediately precedes it in memory and the perceptual weights of the individual features. So the influence of the memory window is dependent on whether its trend matches what's going on in the attentional window or not. So the idea is that, for example, if you have a pretty long, clear crescendo over 5 bars, it's going to have a far more significant impact on tension than like a little micro crescendo over 3 notes. So that was kind of the idea behind how the model worked. And I tried to do a mock-up of the model to give you an idea of how it works, but it kind of presents a toy model. But unfortunately, I kind of did this, and even this image confuses me. So I will try to quickly explain how this works, but maybe it might give you a little more insight. I figured it's better than throwing up an equation or something. So you have a bunch of features. In this case, I just call it feature 1, 2, 3 with some random weights. And then you have the gray dotted line. I don't know if you can see it. This thing, for example, which represents the cumulative slope of the memory window, cumulative slope, this dark line, the cumulative slope of the attentional window. And then you have the actual slope of the tension trend. Sorry, the dotted line, which you can't really see here, is the cumulative slope of the attention window because this is the very first window, so that's why they're the same. So the idea is that you have this moving window in time. It's like a moving average filter, in a sense. And you're integrating these different moment-to-moment cumulative tension trends. So it's a predictive model, and I basically tried a bunch of memory and attentional window sizes. So the memory window ranged from 0 to 8 seconds, and the attentional window from 1 to 8 seconds or so. And what I did was I correlated the predictions with the empirical data. And I graphed the correlation values here just to see what it looked like. And so the different colored lines represent the different memory window sizes from 0 to 8. And here on the x-axis you have the attentional window durations going up to 8 seconds. And these are the R values, the correlation values. So as you see, there's a very clear peak here. These are very high correlation values. Around 3 seconds for the attentional window, and also 3 seconds here for the memory window. So I use that kind of, for this case, as my optimal windows, durations. And here's an example of two of the mean tension responses from the experiment. These are the 2 most complex examples. They're about a minute long. And you can see the empirical data is in the solid line, and the predicted tension from the model is the dotted line, and it actually matches the empirical data fairly well. And you can see why the correlation values are very high. And of course, this is not like the regression model where you use a big chunk of it as training data. There's no training data here. Okay, so that was the model. But now you might be asking, what about timbre? Right? Isn't timbre pretty important for tension? Well, of course it is. I mean, any composer would say that. It's an extremely important part of tension. So timbre, as defined by Vic Adams, is something that covers many parameters of perception that are not accounted for by pitch, loudness, spatial position, duration, or even by various environmental characteristics such as room reverberation. So prior work on tension, timbre's contribution to tension is actually fairly minimal. There's a lot of work on timbre, of course. But in terms of timbre's contribution to tension in particularly, what I found really only explores roughness in particular. So I talked to a bunch of my MIR colleagues who know a lot about timbre because they, that's kind of what they do. And I came up with 5 particular features that I really wanted to look into when it came to tension in particular. Inharmonicity basically describes how partials are offset from integer multiples of the fundamental frequency. Roughness, which is described by Plomp and Lebelt from their 1965 paper as sensory dissonance. Spectral centroid, which is often correlated with brightness of a sound, but they're not synonymous. And spectral deviation, also termed spectral spread, which is the spread of energy distribution across the spectrum. So a single sine tone, for example, has no spectral deviation. Spectral flatness or noisiness, which is defined by how similar a spectrum is to that of white noise, so versus pitchedness on the other end of the spectrum. And my general design for these timbre experiments was to generate 2 extreme states for each feature, like one with no harmonicity, state A, and state B with lots of inharmonicity. So that was the basic idea. So let me play some stimuli for you. So in my first experiment, I designed stimuli that morphed from state A to state B. So that was all like generated in MATLAB, basically. So here are some examples. This is in hold on. Whoops. I think I'm running out of time, so I'm going to just skip through some of these. I'll just play the spectral centroid. So, despite my best efforts, it was actually very difficult to control for pitch and to some extent for loudness as well. Furthermore, these features can co-vary. In other words, it's impossible to just isolate one of these features and have a morphing stimulus that just morphs that feature over time. So at this point, I realized that if I really wanted to test these features, I needed to create static states and have comparisons between those. And so that's what I ended up doing for another experiment, where I just took state A and state B in static forms and asked listeners, okay, what's more tense, state A or state B? So for example, roughness. This is spectral centroid. Spectral deviation. Spectral flatness. Okay, so you get the idea. To make a long story short, the results of these experiments did show that all 5 features contributed to tension. And these experiments are actually still ongoing. I've run 4 of them so far using stimuli that are a lot more complex than these basic sorts of sounds. I've used real music, so electronic music by Stockhausen and No-No. And so the goal is to incorporate this, what I learned about timbre into the general tension model that I described earlier. Okay, that leads to my third commentary, which is that MIR can be used as a physical measure of the information available for human cognition in the musical signal for a given task. This is a nice quote from a paper by Aucouturier and Bigon from 2012. And this measure can be used to control stimuli and separate what's in the signal from what's constructed out of it by cognition. And for my timbre experiments, the MIR techniques were extremely useful for analyzing the stimuli. I mean, there's really no other way I could have done it objectively. So I could basically analyze all of my generated sounds using the MIR toolbox. I used the Genesis loudness toolbox. I used some other MATLAB toolboxes, some libraries that were available, to basically define what these 5 features look like for every single stimulus. So then I can talk more intelligently about the responses and why, and theorize a little bit about why listeners responded the way they did. But due to lack of time, I'm just going to skip to the next issue, which is kind of a different perspective, and it's more what Frank was talking about, which is how can music cognition inform MIR techniques? So what in the timbre experiments, it was kind of the opposite, right? I was using MIR techniques to aid experimental design and analysis. But we could do the opposite. So this is what I'm going to talk about next. Using theories of music cognition or empirical data from experiments to improve or evaluate MIR algorithms or techniques. So one very straightforward way of doing this, and this might be pretty obvious to all of you, is to use more relevant ground truth data to train and to evaluate MIR algorithms. So rather than using a data set that's annotated by one human, why not use, for example, a data set annotated by 5 experts? Right? Because everyone will have kind of a different perspective, and you might get a very nice hierarchical output that you can use in a different way. So that's a more perceptually valid way of evaluating an algorithm based on ground truth. Another way is finding more perceptually valid ways of evaluating how well the ground truth matches the results. So a little bit of a different perspective there. Another possibility, although this is not really very generalizable, but I bring it up anyway because it's highly task specific, is to use cognitive constraints within MIR algorithms. The work I've done with Oriol Nieto, who by the way is now working for Pandora, is a very good example of this sort of approach. So one project we worked on extensively was the automatic extraction of musical patterns. And the reason why I was really excited about this project was because, harkening back to Hyperscore, I wanted to find an automatic way of extracting musical patterns from some pre-composed material. Because as you saw with Hyperscore, it's purely generative. You have users that input in patterns and draw with those patterns, but the system has no idea how they were created, or has no concept of the fact that they're repetitive and that they're important to the context of the music itself. So that's the reason why I really wanted to find an automated way of doing this. So our algorithm is really a data mining approach, so it's an MIR approach, but it uses certain perceptual grouping principles to help weed out bad results. We also evaluated the algorithm by comparing its output to the results of an experiment where we had musicians label a bunch of excerpts by what they thought were the most prominent motives in the musical texture. So the algorithm was originally implemented for symbolic output only, but this was extended to audio input as well, both monophonic and polyphonic, by using a method typical to the task of audio structural segmentation, which I'm sure all of you or some of you have heard about, which is converting the musical representation into a chromogram, computing this self-similarity, key invariant self-similarity matrix, and then extracting the most prominent repeated segments by analyzing the matrix diagonally. So that was kind of the basic approach. And then these segments can be filtered following perceptual rules. So here's a very simple example. Say you have a segment of music and there's a huge rest in the middle. Well, Gestalt theory suggests that, well, it's probably not a motive because there's this big hole in the middle, and so it's probably 2 separate entities. So why waste your time? Why waste computational power looking into that when you can just throw it out? It's very basic, but it's also kind of ad hoc, right? It's a rule that's implemented, so it's not very generalizable. So that's kind of a caveat there. Okay, So quickly, a little bit about another project. This one I did both with Ori Nieto along with Juan Bello and Tristan Jeong. We explored the relevancy of F measure for evaluating the results of algorithms. So, Frank, how much time do I have? Because I don't want to, go over.
Let's say 5 more minutes.
5 minutes. Okay.
Does that work?
Yeah, no, that's fine. I think maybe. Yeah, no, that's
I
fine.
don't want to rush the talk. This is a very flexible program. 10 minutes.
Okay. Well, definitely no more than 10 minutes.
Good.
Okay, I'm nearing the end here. Don't worry. Okay, so with this project, we wanted to raise the awareness of the limitations of the F measure in the context of a very specific problem, which was related to the musical pattern parsing. We were trying to determine the quality of the boundaries found by automatic segmentation algorithms. So segmentation algorithms that divide a piece, say, into sections, into phrases, that kind of thing. The F measure is also known as the hit rate. It basically gives equal measure to two particular metrics, something called precision and another metric called recall. So what precision is basically the proportion of boundaries found that are correct. So say you have like some song and then you have some annotations that indicate boundaries. So something with high precision locates correctly the boundaries. They don't have to be all of the boundaries, but as long as most of them are correct, that's high precision, essentially. High recall, on the other hand, is about how many of those original annotations are actually found by an algorithm. So they don't have to, for example, be actual hits, so to speak, but as long as you have, a whole bunch of these annotations that are actually found, then that's considered high recall. So if you had, for example, a boundary every second, then that's like 100% recall. Or if you had a single boundary that matched an annotation, that's 100% precision. So that's the idea behind it. So the formula for F measure, which is the harmonic mean between the two, rates them equally, which is problematic because humans, from what we observed, tended to favor precision over recall. And because the F measure is used as a way of perceptually evaluating the results of these algorithms, we found that problematic. Okay, so basically what we did was we ran a bunch of experiments using different musical excerpts, and then we generated a bunch of boundary annotations using state-of-the-art algorithms, a whole bunch of them, along with human responses or human annotations. And we simply asked the subjects, okay, what do you think about the quality of these boundaries? Rate the quality of these boundaries. And what we found was that the F measure was not a really good indication of how humans thought the boundaries worked well or not, but high precision was. So based on those results, we offer a new metric that's based on the F measure that weights high precision more than high recall, essentially. Okay, so this is my last commentary, so I'll wrap up my talk now. We often think of individual research projects as very specific and perhaps self-contained, relatively self-contained goals. But ideally, they can also be incorporated into a larger whole, or in this case, and what I'm going to talk about, an application with a more musically creative goal. So to finish up my talk, I'm going to discuss more generally about how all these disparate projects I've mentioned can hopefully contribute to a single computer music application and perhaps in part answer the question that I'm posing in my talk title. So the idea here is that various MIR and music cognition models could really be used to build a truly quote-unquote intelligent computer-assisted composition system. Okay, so here is my graphical score interface of the future. This is a mock-up, by the way. This is not real yet. So this system is currently in the very early stages of progress, and it retains the concept, if you recall, of the motive and sketch windows of HyperScore, but it expands upon them considerably. And so my goal is to design a computer-assisted composition application with graphical annotations that are bidirectional. So for example, in HyperScore, you drew a bunch of stuff and music was generated, right? But say you wanted to go the other way. Because, and this kind of goes back to the project I mentioned about the automatic pattern recognition or pattern extraction. Say you have music already and you want to render a graphical score of it. You should be able to go both ways. And that's very fundamental. It's actually very hard to do also. And I also wanted to implement both analytical and generative tools that interact. So in this case, let me just kind of describe what you see here. So you have this sketch window, right? You draw some annotations that map to motivic material. Great, wonderful. And maybe there are some stuff that doesn't map to any motivic material, because not everything is, a bunch of patterns. There's a lot of filler or transitions or, I don't know, stuff that's not motivic. And then you have these, what I'm calling functional windows. So the idea behind the functional windows is that they attach to sketch windows, and they're analytical, but they can also provide some generative input. So what I mean by this is, here you have a generic kind of general tension line, which is derived automatically from what you've written in the sketch window. And then you have a breakdown based on individual features, loudness, harmony, blah, 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 of this tension line. And then you have harmonic analysis here, which kind of, in piano roll notation, say sketches out, what the computer thinks the harmony is, or implied harmony, or maybe it's not implied, directly from the notes. The idea is that you should be able to manipulate any of these analyses and then update what's in the main sketch window. So say I wanted to kind of tweak this tension line so I don't have this big climactic moment here, but it kind of dips down there. So the system should be able to help you do that by manipulating the various features and regenerating music based on what you've drawn. And then the graphical annotation should update accordingly as well. Or say you just want to tweak one of those particular parameters. It doesn't have to be tension in general. You have a very specific idea. I just want loudness here to be, the dynamics to change a little. Then you should be able to do that too. And then everything should update accordingly. Or say you want to change the harmony. One chord, fine. Then everything should also update. So that's the idea. It's a system that ideally would allow both novices and professional composers to do as much as they want or do as little as they want with a kind of an intelligent, intuitive, musically intelligent computer partner. So that's kind of where I'm going with this. And the tension model will be the most important of those functional windows. And I will implement some version of the model that I talked about earlier in my talk. But the feature descriptions will be automatically generated using MIR techniques, which makes sense, right? Because if you have it's not going to be just MIDI also. It's going to be MIDI or audio or any kind of input, whether it's symbolic or not. But the idea is that at some point it needs to be converted into some sort of symbolic representation internally. Otherwise, it's very hard to manipulate. But that's where the MIR techniques come in. They're very useful. Okay, so although I am most interested in this tension functionality, the software framework that I'm hoping to build should allow for any kind of functional window. So basically any kind of additional musical transformation or analysis. And I really would like this to be open source so that if anyone wanted to make their own module or functional application, they should be able to do that. So I know that sounds kind of pie in the sky, but it's good to think big. And of course, like the whole idea of breaking down hyperscore pieces into motives will utilize the algorithm that I worked on with Uri Nieto to automatically extract motivic patterns from either pre-composed material or audio files or whatnot. Okay, so to sum up everything, I guess, the idea here is that high-level cognitive models like the tension model will enable composers, regardless of their musical background, to have this extra high-level knob into the music that they're working on. Whether it's simply just, have an analytical perspective, oh, this is what, the tension profile is for my piece, or to actually be able to tweak those knobs and to have a direct effect on their music. Now, of course, there's a very long way to go on this project. I realize that, but I really think it'll put together a lot of what I've done over the past years. And when I say that, I really mean it in an integrative fashion in that it will incorporate a lot from music cognition and also from computer music and MIR. Okay, thank you.
Thanks so much, Mary. That's a great vision. Questions?
Yes.
I have a question about your musical tension. Did you ever think about exploring into rhythmic tension, like how in jazz or like where the soloist would play behind the rhythm section had tension, or maybe like polyrhythms where you're playing 3 and 3s over 4 and kind of that, and it takes 3 bars to resolve to get back to the 1 and that kind of thing?
Yes, I have thought of it, and that's a very difficult question. And the hard part of it is it's very difficult to isolate from everything else that's going on. Even something as basic as onset frequency can really throw a wrench into the works. Because it could be that you have a syncopated rhythm that all of a sudden just uses more onsets versus something that was using fewer onsets is a little more square sounding. And of course there's going to be more tension, but it could be from both aspects. Yeah. The syncopation and the additional onset. So being able to kind of tease those apart that's really hard. I really struggled with that, actually.
I can imagine it.
Yeah. I mean, if you have any suggestions, I'd be happy to entertain them.
Thanks.
Yes?
I'm sure there's been some interest in using this as a tool for teaching children.
Yes.
Can you comment on, has there been any kind of development of that, or?
Do you mean the original version of HyperScore or what I'm working on now?
Either the original or current.
Well, actually, the original version of HyperScore, that final version that I demoed, that one was intended to be used for kids in particular in an educational context. It was part of a much bigger project that my advisor at MIT worked on called the Toy Symphony. And the idea was that kids would use these various tools, whether it was software or hardware, and create music or improvise music or do something with music that they normally wouldn't be able to do because they just don't have the musical training. So in the case of HyperScore, what I wanted to provide them with was an interface where they could start sketching out the large-scale structure of a piece, which it's very difficult to do if you don't have any musical training. And it's something that grad level composers talk about with their professors, right? Oh, I'm doing this and I'm shaping the piece here and there. And you can't talk about those things unless you have a whole lot of musical training, usually. So this was kind of a way for kids to have a window into this more high-level creative process, not just writing tiny little bits of music. So that was part of that project, and the idea was that the kids would spend a week using HyperScore. They would have their pieces transcribed. I did the transcriptions for orchestra, and then the orchestras would perform. So it was a very cool project. We went to Dublin and Berlin and Glasgow, and I think since then, the software has not been developed further, and I've moved on to other things. But I think my old advisor is still using it for lots of projects with the general public. But education is very important, and in fact, I am hoping that as I develop this new software, that it will play a very important role in its funding and also the way it develops in the future.
Yeah, it seems to me that graduate students could use the new future version of HyperScore to learn about models of musical tension
Yes.
or other, and all of us could have a kind of a deeper insight into these models, even though we understand them in an abstract theoretical sense. To be able to analyze and then synthesize gives you this intuitive feeling that would be neat.
And I do think composers do this intuitively. All composers have a sense for how they're shaping their piece and how the listener is going to feel about it. But they do it without thinking about it. It's just so basic. So hopefully by visualizing it, it'll really, especially for novices, give some insight into that.
You mentioned other functional windows. The ones that came to mind immediately were to do with emotion, because we're thinking a lot about emotion. So there are models of emotion that involve 3 dimensions, and that's you need to protect yourself from these viruses. They're nasty. So arousal, tension, arousal, energy, and valence is one way in which emotion has been parametrized. Mm-hmm. So you currently have the tension
arousal,
and I think some of those same signatures that you're pulling could inform
The energy arousing.
And the valence is tricky for everybody.
Yeah,
But-
I have to say, Frank, one reason why I've avoided real explorations into music and emotion experimentally is because it scares me.
Yeah, yeah.
The whole valence thing is another story. I feel like with tension it's more objective, and it's something that I can easily kind of get my, I just find it a really difficult topic.
And tension from a generative standpoint, it's not like your hands are tied. Like there's lots of possibilities.
Yes,
Yeah.
and that's what makes it fun too.
Yeah.
And so you can also, ideally I want the system to be able to keep generating new versions based on those parameters. So if you don't like what it did, you should ask it to do it again. Right, isn't that what you do when you're working with someone?
Can I ask about, just take it back to the end of high school. What's going on in the harmony window when you're applying that? Because all of a sudden, what was sounding very atonal sounded very organized.
Uh-huh.
And how prescriptive is the manipulation of the motifs to create that?
Oh, I would say it's fairly prescriptive on one level and less prescriptive. So there are two basic ways that steps that happen in the process. One is that it actually generates the underlying progression first. So there's some degree of randomization. Well, not randomization. It really depends on the texture of the line.
Does it analyze the motif to generate that harmonic progression in some way?
No. It's completely based on the tension line, the way the user draws that line.
Right.
Which is, by the way, a problematic aspect of the software because it's very poorly implemented. It's a bad physical model that doesn't work very well, and I would redo that whole thing. I wouldn't do it now. But then after the underlying progression is generated based on the shape of the line, then it's really prescriptive. In the sense that depending on the way I drew the demonstration piece was intentionally meant to be very square, but how it harmonizes or changes the notes within each original, motive or motivic material depends on how it falls on the beat, what's the meter, underlying meter, is it going to be a chord tone or is it going to be a passing tone? Like those kinds of considerations are important for how it generates or reorders the notes, I guess. But it's not the most amazing algorithm in the world, trust me. It kind of worked for what we wanted it to do, but I was never very happy with it. And in fact,
I'm not accusing it of being the demo button on a Casio keyboard, but it obviously it's doing much more interesting things than that. But.
Well, I did use the progressions themselves were taken from Bach chorales.
Sure.
I figured that was the easiest thing to do.
Nice.
Okay, so in the interest of time, we are going to move on. Thanks for all that reflection and summary of this work. Thanks again, Mary.